Yeah, so welcome everyone. This is the second part of our five-part intro to learning, or rather, our neural networks series workshop. And this part is where we briefly introduce gradient descent and also backpropagation for deep learning. Can you go to the next slide? Yeah. So as a brief agenda of what we're going to cover, the first is we're going to review the kind of like topics, the main ideas from topics that we covered in last meeting, which are essentially just like the vectorized neural networks. Then we're going to cover motivations for gradient descent and intuitive visual explanation for gradient descent, and then gradient descent formulated mathematically. And then after that, we're going to transition directly from gradient descent into backpropagation and also a very toy implementation of backpropagation, just so you kind of get like a gist of how backpropagation works. So I guess to start off with, just as a review, we can kind of consider at this point in our knowledge that a neural network is kind of just like a black box in the sense that you get an input, such as like a dog picture, and you want to output the probabilities that it's like a dog or a cat. So this is a very toy example of an application of neural networks. But considering them in much more mathematical terms, we can convert a picture into just the pixel values, and then we apply a function to it, which determines the probability that said assortment of pixels is a dog or a cat. And then we can kind of expand this function term, into being more along the lines of a neural network, specifically in the form of neurons. And as we can see, each of the input layers, the 255, 75, are applied with a weight and then added together with some bias, and that will output the result. And then, yeah, so for each kind of like neuron in the subsequent layer, i.e. kind of like the second layer, all of the neurons from the previous layer are connected to the neurons in this layer, which is why another word for kind of like multiple layers is fully connected layers in like deep learning. So yeah, those are like the functions for how the whole process works. So as a reminder, A is the activation function, W is the weight connecting the input neuron to the output neuron, and B is the bias term that kind of dictates the magnitude or the weight of said neuron. And in more simple terms, or in a vectorized form, we can compute it as just a Wx plus B term. Yeah, so those are kind of like the code examples of how we can do that. So now we go into the motivation for gradient descent. So just kind of like a review. I don't know if all of y'all took math, I think math 20C or something like that, where they cover gradient. So we'll just briefly touch on what a gradient is. A gradient is essentially kind of like a plane vector pointing in the direction of the steepest slope, i.e. the grade of said point. So if you look at that picture of some like really curvy function, the gradient is going to be pointing down towards the bottom of said function, and that is the gradient, or rather the opposite of the gradient, because the gradient is actually going outwards. And then gradient descent is the optimization algorithm used most commonly in deep learning. And what this does is an optimization algorithm that minimizes some function by moving in the direction of the steepest descent, which is negative of the gradient. And so intuitively, why gradient descent works is because, as kind of like we reviewed before, a neural network is essentially just a really complex function in a really high dimensional space. Kind of think of like a one layer, if we think of the example of a one layer neuron or one layer neural network with X neurons, this can model a function in X plus one dimensions. So kind of like, let's suppose you have a one layer neural network with like two neurons, then we can essentially model a three-dimensional function because one could be A, B, and then the output would be C kind of thing. And so kind of like a vector fed into the network would generate a unique vector output somewhere on this function. And as a result, we would need a metric for optimizing this vector output compared to the actual output. And so that is where essentially gradient descent comes in, because we would first define a loss function L that determines how different the actual output is from the expected output. And so gradient descent allows us to reach the minima, which is not necessarily the global, by finding optimal parameters for the weights and biases and other kind of like gradientable parameters in the neural network based on the loss function L. And so kind of like intuitively for any output, difference between actual output and expected output should be close to the minima at the end. And so now we're going to kind of look at a more intuitive, a more visual-based explanation of gradient descent. So let's suppose this is the function that we have. Off the top of my head, I don't remember what the function is. And let's suppose that little turquoise dot is the start of the loss. So we can see that the start of the loss is pretty high in the sense that there's a large difference between the initial point of where our function wants to be, or between our input and also our output with respect to the loss. Yeah. And then as a reminder, we want to go in the direction opposite of the gradient. So for this function, we would be traveling downwards. So yeah, we can see that because the gradient is the highest delta, it would actually be pointing upwards. So instead, we would be traveling directly downwards. And so the loss after training is going to be at the bottom of said function. But it's really important to note that most neural networks, if you get a really big neural network, it's not going to be this intuitive in what it's supposed to be. Like you won't be able to visualize a lot of neural networks in a very efficient way like we did here. And as a result, the function is going to be much more complicated, and there's going to be some global and also there's going to be local and also global minima. And we aren't 100% sure whether we reach a global or a local minima after training.
Okay, so now we're going to be putting some math to this behind this intuition. So actually, let me first go to a whiteboard. So again, like we'll just start with a simple example, right? So pretend that we have, maybe some data. Let's say like, we just have some data points. Maybe it's like somewhat linear. And maybe at the start of training, we have some model that is like, I don't know, like that, right? So obviously this function right here, this function f, I'll just say this is x, is obviously not a very good model, right? And so as Edward described, we would usually have some kind of loss function L, right? And so in this case, we can use maybe a loss function called mean squared error, right? So MSE, mean squared error. And mean squared error is basically if you look at sort of for each data point, like what is the distance between a data point and our model, right? You do that for all the points. You want to penalize for large distances, right? So one way you could do that is, let's say this is, each point is like yi, right? And then we could say, what's the difference between yi and f of, hold on, at some point x, xi minus f of xi. Okay, I'll make that a little more clear. and then you would just square this. So basically, you would just sum this over, like I go 1 to maybe have n data points. And since it's mean squared error, we can also divide by n to get an average, right? So you'll see that, like, this is a pretty bad model, but if we had something that was like, something that fit the data better, right? And maybe there's like more, the dots are closer to the line, then obviously our mean squared error is going to be a lot less, right? So really, like, what the problem we're trying to solve is, can we find a good f such that L is minimized, right? Or you could say like min L and over the parameters, right? So for here, f could be like, mx plus b, right? But you could also say wx plus b. Usually we use w for weights in neural networks. So, let's see, I will just do a capital W. This is going to symbolize lowercase w and also b, right? And L is parameterized by w. Yeah. So basically, we just want to find a function such that our loss is as small as possible. And so we're trying to find w over, hold on, get more space here. So we had this, like, right, in 3D, this axis is our loss. And then this space is like, this could be like W or B, right? And so we just want to solve for this, right? We want to find that special point. And, maybe if we're starting at our initial very bad function here, that could correspond to some point here, right? And so this is just an optimization problem, right? And there's actually an entire field called numerical optimization dedicated to solving problems like this, right? And if you're interested in more of this, you could go to workshop 3. We're actually going to look a little bit more into this area. But for now, we'll stick to gradient descent. So the next question is, well, how do we actually solve this mathematically, right? So the issue is, this function in general might not be that nice, right? And when I say function, I actually mean the loss function. The landscape might be something very crazy. So, you could have something that's easily like, very, very insane, right? And furthermore, it might be very high dimensional. So instead of just W and B, you can imagine having like W1, W2, et cetera, B1, B2, et cetera, right? So something you can't even visualize. And so the question is, well, is there a nice way that we can solve this minimization problem, given that our landscape could be very crazy and we could be dealing with very high dimensional space, right? And as Edward mentioned before, that's where gradient descent comes in. Basically, you could imagine, like, if you were stuck on Mars, for example, right? So if you were on Mars, right, here's you, and you were in some really crazy terrain, right? And basically your task is to find lowest point, right? Well, practically speaking, all you have is really local information, right? Like you can only, your visibility might be limited to some radius, right? And within this radius, you can see that, well, if I just traveled this direction, I might get to a low point here. It might not be the lowest point in all of Mars, but it could be maybe a good approximation, or maybe not even a good one, but the best that we could find given our limitations. So in math, right, we have this loss function. And so we want to minimize this. And the only information we have is sort of our local gradient, right? And so from calculus, that would involve actually taking like the derivative of this mean squared error. So I'm going to go back to these slides. So here's the mean squared error function. And you also note that there's this 2 right here. This 2, it doesn't actually affect anything. It's sort of there so that when we take the derivative, the square moves down and it cancels out nicely. So don't worry too much about the 2. So let's go to the next one. Oops. Yeah, so we've sort of described what the task we want to do. So we want to find some direction to move in our basically our landscape here, such that we're making progress towards the lowest point. And here we sort of denoted the direction as v, some direction. And our goal is to choose some good direction, right? So we obviously don't want to go the wrong way. We want to go the right way. And the gradient is, well, as we will see, the point that mathematically we can say is the best direction, at least locally. Right, so again, our goal is to sort of decrease L and find some direction V that does that very well. And so locally, the best direction we can choose is sort of what we're trying to find. So first we can sort of say, well, if we go in any direction V, right, how does that affect L, right? And here we've just denoted the change in L, right, delta L, and approximately, at least for very small v, it works out to something like this, right? So it's just the partial derivative in each dimension, in each direction that you can take. Sorry, in each, yeah, I guess each dimension is a better way of saying it, times a very small step in that direction. And the sum of it, you can see these kind of cancel out, these small changes in VI will give you the total change in the loss. So if we want this to be decreasing the fastest, if we want L to be decreasing fastest, then obviously delta L has to be very negative, right? So it's very large and negative. And so here we kind of just rewrite this thing in vector notation. So this turns out to just be a, just a dot product between 2 vectors, right? The first vector is the first components here. And the second vector, we just captured all these delta V's. And so this ends up just being a dot product, right? Between all these partial derivatives and our direction. And coincidentally, or maybe not, this turns out to be the gradient, like the definition of gradient from vector calculus, right? It's just a partial derivative of your function with respect to every single dimension. And so it turns out that there is a handy identity for your dot product in terms of the angle between the 2 vectors. So you can imagine like, your gradient vector is pointing in some direction, and then the direction V is pointing in, whatever other direction, and that there's some angle in between them. And it turns out that, if our goal is to make delta L as negative as possible, then it turns out that we can just pick a V that gives us this property based on this identity, right? So how do we do that? Well, first we should discuss our limitations, right? So our approximation here, remember, only holds true when V is very small, right? It only holds true for infinitesimally small changes in V. And so basically, one limitation is that V should be fixed to be a very small size. So we can't actually change the size of V, but what we can change is the direction, right? This theta parameter. And so it turns out that cosine theta is sort of maximized when theta is either 0 or 180. And in the case where we want to make cosine theta negative, since these magnitudes will be positive, we needed to make it 180, because that's the only one that gives us a negative value, right? Because cosine 180 is -1. So basically, that means that V needs to point in the opposite direction of our gradient, which means that V should be some negative multiple of our gradient. And that's how we sort of capture down here. And so this sort of gives like the mathematical proof that the best direction possible for V is to go in the negative direction of the gradient or opposite the gradient. Okay. And so as a reminder, like V is sort of a vector that captures every single parameter that we have in our model. And so here I've sort of written in component form that each parameter would basically be changed by some multiple, some negative multiple of the partial derivative, right? And so there is a term for this sort of symbol right here, which is the multiple, and that is called the learning rate. And the learning rate is usually this, what we call a hyperparameter, meaning that it's sort of up to you to choose a good value for this, right? So you can imagine that if your learning rate was very large, the magnitude of this would be very, very long, right? And, for example, here, you might overshoot if it's a little bit too long and completely miss the minimum. So that's why it takes a bit to find the actual good value of the learning rate for your problem. And so at this point, we just need to find somehow this partial derivative. And so here we just have an example, right? So we're still using mean squared error, which is right here. And we want to take the partial derivative of this with respect to some parameter. And so, I'm kind of gonna bust through this, but basically you would just apply chain rule, right, from calculus. And you can sort of go over these steps on your own time. But basically we would just do chain rule. And at the very end, you would get something that looks like this, right? So this would be our actual derivative right here. And so for each weight, we could just plug that back into our update equation. And this is basically what we would need to follow to change each parameter in such a way that we're actually decreasing our loss. And so if you apply this once, right, that's one step, right, in our landscape. And each step we take, there's a term for that, and it's called epoch, right? So usually you'll hear people say, that they train their model for X amount of epochs. And this turns out to also be another hyperparameter that you can tune. So if you have many epochs, then you might eventually settle into some minimum, local minimum. But if you don't have as many epochs, you might not have reached that point yet. And so another thing to note is that in this formulation, we sort of captured all our data points in the loss function, right? So this is all overall n data points. But it turns out that if we have a very large data set, then this might not be very efficient, right? It might take a very long time to, say, train over a data set of, millions of points, right? And so what we can do is we can actually approximate this portion by, instead of summing over all the data points, we could just sum over a random subset of these data points. And doing this is a variation of gradient descent called stochastic gradient descent, right? Stochastic referring to the random sample that we draw to approximate the gradient here. And that random sample is usually referred to as a mini batch. And the size of the mini batch can also be another hyperparameter that apparently can also have some effect on how well your model is training. And so this is kind of just a note that what we just went over is a very simple example where we're using like one layer. Actually, not even one layer. We don't have any hidden layers and like no activation functions really. But if you were to do a more fancier neural network with more layers and more complicated activation functions, then the overall process is going to remain the same. Like you're still going to take the gradient, but your gradient is going to look slightly different depending on which function you use. And so now we're moving on from gradient descent to backpropagation. So here I kind of just put a, this is just a neural network with no hidden layers. And this is sort of how we would describe it mathematically. Here's a neural network with one hidden layer. And this is how we would describe it mathematically. And note that we can expand the activation from the previous layer into, basically what was right here, right? And then similarly, we could do for two hidden layers. And basically, the point of these slides is to show that there starts to become a structure when you actually expand out, the full function of the neural network, right? And the point is that, if you're taking the gradient of functions like these, and you can imagine, neural networks that have many more layers in this, if you apply the chain rule on this, quickly you realize that there's a lot of computation that's going on. And you have to keep in mind that, not only are you taking the gradient of, you're taking the gradient, so you're taking the partial derivative of loss function with respect to every single weight here, right? And that is definitely going to grow depending on the size of your neural network. Oops. And so basically, one thing we can realize is that, for example, if we have a neural network that looks like this, where we have two hidden layers, and we wanted to take the derivative with respect to, say, this weight right here in the final layer, we can realize that if you were to take the derivative, the chain rule wouldn't go very far, right? Because anything that comes before this weight right here, so anything that's like further than W3 here, doesn't depend on this weight, right? So when we take the derivative of this, it turns out that all this is just a constant, right? But if we were to take the derivative with respect to something much earlier, then we have a much longer chain rule, right? And so, we could ask the question like, computing the chain rule every time for each parameter seems like it'll take a very long time. And maybe there are some smarter ways that we can do this so that we can save some, computation time. And so the third insight that leads to backprop is that, if you look at the partial derivative with respect to, these two different weights, right? And you actually see like what, what these weights actually affect a neural network, you see that there's some overlap, right? Like there's some computation that is, or there would be some computation that would be shared when you take the gradient with respect to these two parameters, right? And so the key idea is that if you do the math, it turns out that parts of the chain rule are actually identical for different parameters here. And so what we can do is we can just compute some of these computations just once, memorize them, and then when we need to use them again, we just look up what we saved and just, in constant time, directly refer to that what we already computed before. And so the idea is that since these earlier layers depend on these shared computations from later layers, right? We can sort of work our way backwards, right? So we could start computing these shared computations in this layer, and then in this layer, and then in this layer, and then in this layer. And so what happens is that our computation, because we're memorizing things as we go further and further back, computing the overall gradient for this neural network is going to be linear in the number of layers. So it's going to take O(n), where n is the number of layers. In contrast to if we didn't do this, then we would have to, recompute all these shared values over and over again. And that could be easily exponential time. Okay. So also caveat, so we're actually not going to show the actual equations for backpropagation because we're not too sure if that would be something that we could effectively deliver in the time we have here now. But at the end, we can share some resources if you are interested in actually looking at those equations. There's some pretty good online resources that we can share if you're very serious about studying the mathematics behind how this works. Let's see, Edward, is this your part?
I think you could still go ahead, but first I'm asking the general chat if they have any questions that you guys want Jason or I to address before we go on to like the toy implementation. Okay, yeah, I guess then we can just proceed to the, what if we missed the first? Yeah, I think that's fine, because the first meeting was just covering a lot of like the vectorized. The whole idea was like just vectorized neural networks kind of thing, and just like a general introduction. So if you missed it, don't worry. We have posted the slides into our ACMAI Discord, so you can just check them and review them from there. So as I kind of mentioned before, we're going to send the last of the acceptances and also some of the rejections today. And we will have projects start hopefully next week. Yeah. Okay. Um, so that's all the questions. Then we can just start going over like a pretty toy example of backpropagation. Okay, yeah. So to begin with, we have to initialize the network. One, we need to calculate the gradient for layer 2, biases with respect to the expected output, and also weights with respect to the expected output, and also the input to the layer. And then after that, we would need to calculate the gradient for layer 1, specifically kind of like the biases with respect to weights of layer 2 and also the expected output. So I guess the key takeaway here is that the further back you get into the network, or kind of like if you go in the backwards direction, the further back, you need to calculate the gradients with respect to the prior gradient. So it's kind of like Jason mentioned, the simplest way to understand this is kind of like using the chain rule further down. And so this is kind of like our implementation of said gradient for this type of network. What we can see is that we initially start off with the overall result, which we can see is like P. And then after that, we kind of just like go backwards and compute the gradients at each time step. As seen here, where we just take all of the gradients with respect to the initial one. So what I mean by this is that like dl by dw1 is computed with respect to dl by dh, which is computed with respect to w2, which is like, if you look at the previous slide, w2 is the last layer. Yeah. And then, so this is how we want to do gradient descent. So gradient descent is pretty simple in the fact that we're just updating the weights and also biases based on the learning rate and also the gradient computations that we did in the previous slide. And so this is kind of like how it works in a very, very simple way. And so initialize the network. We initially initialize the network to all zeros, but there are much better ways to initialize the network though. And we will cover that in a later workshop. So after initialization, we compute the kind of the error. And so this one's like the error is like 0.5. And so, yeah, we just continuously backpropagate. As we can see, we start off with a 0.5, then we compute 0.1, 0.2, 0.3. And after that, we go to 0.6, 0.5, and 0.3. And then using kind of like these gradients that we've just calculated, we then just update the values. Yeah. And those are like kind of like the values that we got one time during one of our training epochs. Yeah. So does anyone have any sort of questions at this moment? I guess there are no questions then. Oh, can these workshops carry? Yeah, basically. Or 151B specifically. Oh, 151A. 151A is more along the lines of linear regression and that kind of stuff. So, I think for that one, probably the first workshop is the most useful. 121B covers more along the deep learning aspects, and that will be useful. For like this, the next further workshops will be useful for 151B. Yeah, so does anyone else have any questions?
If anyone thinks of any more questions, feel free to ask in the Discord. Otherwise, I think we'll stop the recording. And yeah, thanks everyone for coming. Hope to see you at the next workshop.